Welcome to the next video on measure theory and probability. This is video 6 on Limsup and Liminf for sets. This corresponds to part 1, chapter 1, section 2 of the textbook. So if we have a sequence of measurable sets in a measure space, then we will define the lim-sup of the sequence of sets in this way. It'll be the intersection from n equals 1 out to infinity, and then the union over the index k starting at n, taking the union of everything after that. Now, this perhaps seems strange. Why would you define lim-sup in this way? And of course, it has to have something to do with the limsup and liminf for sequences of real numbers. And let's remember briefly how one way that you can think about what those things are. Now, for the limsup, if you have a sequence, to get the limsup, you effectively first take the sup over the entire set, right? Then you basically throw away the first term of the sequence and take the sup over what remains. And then throw the first two terms away and do it all over again, and so on, so that in effect, what you're effectively doing is building a sequence of sups where the sups just kind of forget early terms, right? And then you take the limit over that sequence of sups. Well, there is a good analogy with what's going on here for sets. If you think about what's going on here, imagine setting n equal to 1 so that we take the union over everything, right? That's a bit like taking the sup over the entire sequence of real numbers, right? And a good analogy to that. Okay, that's with n equal to 1. Now set n equal to 2, and so we're taking the union over everything from 2 and after, so that's like taking the sup of everything from 2 and after, and then we're intersecting those together, which effectively just means that if anything was in the first set that's also in the second set, well, fine, we keep it, but if anything was in the first set but not the second, then we throw it away, basically. And so, in effect, right, that basically has the effect of throwing away the early terms, right? So there's a good analogy in that way with the limsup of a sequence of real numbers. Now let's illustrate this, right, because this can be fairly confusing, and so let's look at a sequence of sets and compute the limsup, and we'll also get around to discussing the liminf, of course. But effectively what this sequence is intended to demonstrate is a sequence where, some portion of it is shrinking, right? So this, whenever n is congruent to 0 mod 3, which is effectively just to say that it is divisible by 3, so that basically every third index gets you this set. Then you get this shrinking set, right? It goes from 0 to 3 plus 1 over n, but if n is getting bigger and bigger, then this is getting closer and closer, tighter and tighter toward 3 from above. Okay, so that's somewhat the point of this first clause. When n is congruent to 1 mod 3, then we'll just have this constant, 0 to 2. And then I also wanted to have a portion of this thing that is growing. So here we've got 0 to 1 minus 1 over n. So as n gets bigger and bigger, this will tend closer and closer to 1 from the left. And that happens when n is congruent to 2 mod 3. So we've got a portion that's shrinking, a portion that's growing, a portion that's completely stationary. And let's see what happens when we take the lim-sup of it. Well, I claim that the lim-sup is the interval from 0 to 3. Now let's think about why that might be. Well, set n equal to 1, and then we union over everything that you could possibly get. Now, with k equal to 1, we'll first enter this clause, we'll get the interval from 0 to 2. Then with k equal to 2, we'll come down here. We'll get a smaller interval. So since we're taking a union, then we can kind of just ignore that because the union is just going to take the bigger interval 0 to 2. Okay, great. With n equal to 3, we come up here and we get the biggest interval so far. So that this really, in this example, becomes the, like sort of what the union is so far as we sequentially keep taking these unions. And so what, with n equal to 3, we get the interval from 0 to 3 1/3, and that's what the union is so far. Now, as we keep setting n to bigger and bigger values, we keep kind of going through these, over and over again with n bigger and bigger. We'll never again get an interval as big as this, so that really is the union when over here we've set this n equal to 1. Okay, now set n equal to 2, which means that we're now going to take our union starting at 2. Well, if you go through it, you'll just start at this clause, but then you'll come over here, and with n equal to... with k equal to 2 by the time you get around to here, then we'll just get the same set as last time, and everything will just be the same as last time. So with n here being 2, right when we start everything at 2, we just get the same union. So now set n equal to 3. Now we're going to skip this, start here, but we still get the same thing, right, with k equal to 3 here. And so the union is the same, but something happens differently when n is equal to 4. So when this n is equal to 4, which means that k starts at 4, we start here, we get the interval from 0 to 2. Then we get a smaller interval, so we might as well not worry about it because we're taking the union, which gives us the largest set. So far our set is the interval from 0 to 2. Then we come around to here when k is equal to 6, and we get 3 6. And that is now the biggest set that we found so far. So we've got the interval from 0 to 3 1/6. Now, at this point, we can start thinking about how that intersection plays a role, right? We had the interval 0 to 3 1/3 a few times. But now we get the interval 0 to 3 1/6. We're intersecting them, so we take the smaller set, which is 0 to 3 1/6, and that is what this set is so far. It is contracting, it is shrinking, right? It was 0 to 3 1/3, now it's 0 to 3 1/6. As you keep plugging in bigger and bigger n, you're going to continually keep intersecting sets that are shrinking effectively. Shrinking, but always containing 0, and and always containing 3, but anything even slightly above 3 will eventually get eliminated, so this is the Limsup. So I hope, I know Limsup can be fairly confusing. I hope this has made it at least somewhat understandable. You might need to spend some time doing practices to get more and more familiar with it. By another helpful sort of picture, if you think about some sequence, which, I'm just drawing some random diagram of a sequence, right? So this would be like a sequence of real numbers, a sub n, and the Limsup. If you think about some kind of sequence, and here I'm going to draw a fairly, special sequence that's kind of alternating but converging towards 0. What you often think of is that the Limsup is kind of what you get when you take the top edge of the sequence, right? And whatever that converges to, that's your Limsup. And the Liminf is kind of what you get if you take the bottom edge of your sequence. So that's your Liminf. And here, if you think about what we've been talking about, we've got like this set that, like the sequence of sets that is like what you initially 0 to 2, then 0 to 1 minus 1 over n, which I'm going to try to sort of diagram as looking a little bit like that, like a little less, well, I guess it actually goes to that's when n is equal to 2, so like that, close enough. And then when n is equal to 3, then we're all the way out here. And that's it on the first cycle. Then in the next cycle, we again go 0 to 2, 0 to something slightly under 1, and then 0 to something slightly bigger than 3. But, right, like that, okay? And so on. And what you can kind of imagine is that as this goes on, the lim soup is kind of selecting out, sorry, I was not drawing those going towards 3. Sorry, let me correct that. So this one should go slightly above 3. Then this is 0 to 2, 0 to something under 1, 0 to something just over 3. Anyway, so the point is that if you are thinking about the lim soup, it's the thing that kind of selects out the right edge, right? It kind of follows along the rightmost edge of where these sets kind of converge toward, right? So it's kind of, the lim soup is like the top edge, here for the set diagram, here for the sequence of real numbers. So hopefully that makes at least a little bit of sense. We could kind of repeat a lot of this to talk about the Liminf, but basically, right, it's not too surprising that it would kind of toggle the intersection and the union. And but let's actually talk through why the Liminf in this particular case is the interval from 0 to 1 exclusive. So imagine that you set n equal to 1, so that means that you're going to intersect with k starting at 1. So you intersect all of these sets. That means you're going to take the smallest set, and I think we can pretty well understand from this diagram that that's going to be this one, which is the interval from 0 to a half. Coming from this clause, that's the smallest set you'll find when you start k at 1. Now, do it all over again, but set k to 2, right? So you're going to intersect starting from 2, and so that means that we skip this this clause. We get the same thing, right? Because we start here, and we get the same result. So yet again, the interval from 0 to a half. Then set n equal to 3 so that we skip this clause, we start here, that gets you this very large interval, 0 to 3 1/3. But then we come down to here and we take the interval from 0 to 2. Again, because we are intersecting, we take the smaller set, that gets you the interval 0 to 2. Then you come down to here and you're plugging in what, like 5, right? But with 5, you get this interval from 0 to 4/5, basically. And that's even smaller. So actually now that's what the intersection here is equal to. So we now have the interval 0 to 4/5. And we go through this over and over and over again, but you'll never get anything smaller than that interval 0 to 4/5. So since we're intersecting everything, that's the intersection, right? So what we have just talked about is when you start with k starting at 3, you get the interval from 0 to 4/5. And again, right, so like initially it was 0 to a half, and now we're unioning that, right? Now when we're thinking about all of these intersected sets and we're taking their union, then effectively we're getting 0 to a half union 0 to 4/5, and eventually it'll become, union 0 to whatever, 1 minus 1/8, I think. So anyway, but the point is they're growing and growing. They're getting closer and closer to 1, but, and we're unioning them. So this set is growing and growing. It's expanding out towards 0 to 1, getting closer and closer from the left. But the thing is, none of these sets will ever contain the number 1, right? They'll get closer and closer to 1, but none of them will ever actually contain the number 1. And that is why we get this interval from 0 to 1 exclusive on 1. By the way, you can certainly give a completely formal proof of these two equations in this particular example, and that might itself be a good exercise, so feel free to do that if you want to try to work on getting more familiar with this idea of Limsup and Liminf. Of course, right, so a lot of the same stuff could be said about Liminf and Limsup. We forget early terms. And another analogy between Limsup and Liminf is their usefulness, right? So the Limsup, one of the nice things about it is that the sequence of sups always forms a monotonically decreasing sequence, and therefore its limit must always exist in the extended sense, right, where the limit could be equal to infinity. And likewise for the Liminf, it's the sequence of infs forms a monotonically increasing sequence, and its limit must exist in the extended sense. Well, again, right, by talking about Limsup and Liminf for sets, we get these chains, right? The Limsup is, essentially taking an intersection over a monotonically decreasing sequence, and therefore the continuity of measure that we were talking about in a previous video applies to that, right? And for the Liminf, we get a monotonically increasing chain of sets, and therefore we can apply continuity of measure from below, I think. So anyway, so again, right, not only is some of their intuitive ideas, there's a parallel between the set and the real number sequence sort of versions of Limsup and Liminf, also each of them kind of guarantees a certain sort of monotonicity, which then ensures that you can do certain, valuable things having to do with a limit, basically. So at this point, you should feel encouraged to prove the containment that the Liminf is always a subset of the Limsup, which, by the way, is also in analogy with sequence or the Liminf and Limsup for sequences of real numbers. But now we're going to finish with a theorem. The theorem states that the measure of the Liminf has this nice property that you get this sometimes useful inequality. And when the measure of the first union is finite, then the Limsup also satisfies corresponding inequality. And it is no surprise, right? I think, because of what I said earlier, hopefully you somewhat anticipate that this ought to have something to do with continuity of measure. But let's go ahead and start getting into the proof. So let's take the Liminf, let's start from the left-hand side and take the measure of the Liminf. And that is just notation, right? So this equation just comes by definition. And as I pointed out, this sequence of intersections with bigger and bigger n effectively gets you a monotonically increasing chain of sets, and therefore continuity of measure tells us that we can take the limit of these these measures, which in this particular case would be the limit of the measures of the intersections. Now, we're not all the way to the other side, and in fact, we don't even have an inequality, we just have equalities at this point. So what do we do from here? Well, I think it's pretty clear that we effectively want to take this measure of the intersections and somehow sort of get an inequality with the infima, because if we could, in a sense, kind of exchange out that portion for the infima, then you'd have the limit of the infima, and that would be the Liminf. So that's what we want, right? I hope it makes sense that I am claiming that this is what we want. If we have this, the proof is complete. So how do we get this inequality? Well, notice that when it comes to an intersection, right, if you intersect a whole bunch of sets, that intersection is always a subset of each one of the individual sets. Therefore, by the way, I believe that this inequality is called monotonicity. I probably should have said that when I introduced it, just forgot about that. But since we use this so often, I probably ought to give it a name, so let me go ahead and do that now. So it is this property that if one set is a subset of the other, then it has a smaller measure than the other, in this weak sense. This rule is called monotonicity. So here what I'm doing is I'm applying monotonicity. So by monotonicity, I get this inequality. And then what this necessarily means is, since this is true no matter what k is, then therefore this quantity is a lower bound on the set of all of those things for each possible choice of k, right? So we have a lower bound, effectively, is what I'm getting at. Well, the very definition of the infimum of any collection is that it is the greatest lower bound, that it is greater than or equal to any given lower bound. And therefore, we must have this inequality, which was exactly what we had hoped to demonstrate. And from here, the rest of the proof I have already kind of explained verbally, so I'll leave, if you want it written out in detail, I'll leave that to the viewer. I won't go through the case for Limsup because it is nearly identical.